So I want to start with a summary of what we did last time, and then we'll start talking about Chapter 2. Also, it's a long lecture, an hour and 50 minutes. I think we might just end early rather than take a break. If people feel strongly one way or the other, just let me know. And please let me know if the sound quality gets really bad, because I'm underground and there's just activity around me. And also, they're doing work on the network, so it's not impossible that I drop out. So in general, the policy for this course will be, let's say if I can't connect in like 15 minutes, and you don't get an email from me, that you can assume class is canceled. But hopefully that won't happen. All right, so let's start with a summary of last time. So last time we introduced the formalism of analytic mechanics. So it was mostly a bunch of definitions and review. So one of the important concepts that we introduced was what we call the number of degrees of freedom. For a system. And so the number of degrees of freedom is the minimum number of scalars required to describe a system. So in general, for an unconstrained system, so for a system with no constraints, the number of degrees of freedom, which I'm almost always going to call with the lowercase l, that number of degrees of freedom would be 6 times m plus 3 times n, where capital N is the number of point particles, so in general, a point particle requires 3 numbers to describe its state. So we describe its state by describing its position, and you can always think of things in Cartesian space. For a particle, you need 3 numbers to specify the position of the particle in 3-dimensional Cartesian space. M is the number of rigid bodies So a rigid body is a collection of particles that are fixed in position relative to each other. So to describe completely the state of a rigid body, you need 6 numbers. For example, 3 of those numbers could be the Cartesian coordinates of the center of mass, and 3 of the numbers could be rotation angles to describe how that rigid body is rotated. sometimes constraints effectively reduce the number of degrees of freedom. The number of degrees of freedom. So for each constraint equation, you have one less degree of freedom. So an example of a system with a constraint is if you have, say, two masses that are connected with a massless rigid rod, the unconstrained system of two masses has 3 times 2, so 6 degrees of freedom. However, you can write a constraint equation between the position of the two masses that the distance between them has to always be equal, say, L, the length of the rod. So you can write a constraint equation, if this is mass 1 and mass 2, you can write a constraint equation of the form something like x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared equals L squared. And so with this, what we call constraint equation, you can eliminate, for example, one of the variables and re-express it in terms of the others. So there are less degrees of freedom required to describe the system. So in this case, the system can be described with 5 degrees of freedom. So for a constrained system, so for a system with constraints, the number of degrees of freedom, n, would be given by 6 times capital M plus 3 times capital N minus lowercase k, where lowercase k is the number of constraint equations. So that would be the main points that we covered in the lecture last time. We also looked at different types of constraints, and we defined them, or introduced new terminology based on whether those constraint equations have sign in them, and based on whether those constraint equations contain the coordinates for inequalities or velocities. In particular, the kind of constraint equation as the one that we've just written here in the example, the kind of constraint equation that we like are those that are called holonomic. Those are constraint equations that are between the coordinates and contain an equality. So they straightforwardly allow you to express one coordinate in terms of the others and make it very clear how the degrees of freedom reduces. Okay, so are there any questions about this material? Okay, so if there's no question, let's move on to Chapter 2, the calculus of variations. So this will be a relatively, I guess, a dry chapter because it's all mathematics, but it's an important basis for the rest of the course. So I suspect this chapter will take us maybe into next week, presumably. We'll see how fast we go. So all about analytic mechanics is really based upon the mathematics of the calculus of variation. The goal of the calculus of variation is to study what we call stationary values of integrals. So the goal is to study the stationary values of integrals. And that's really what calculus of variation is. If we study the stationary values of functions, that's called calculus. So the stationary value of a function, let's say you have a one-dimensional function, y equals f of x, then you know that if you look at points where the derivative is 0, we call that a stationary point. And then you can look at the second derivative, and you can find out if that's an inflection point, or a minimum, or a maximum. In the calculus of variations, we have the integral of a function, and we'll be interested in knowing under what conditions is that integral what we call stationary. So it's like saying when is the derivative of that integral equal to 0, but we'll call that the variation of the integral. All right, so that's sort of the high-level picture. So now let's get into it, and we'll apply the techniques of the calculus of variation to functions first. So we'll do calculus in a more complicated way, so that when we then apply it to integrals, hopefully by then it's cemented in your minds how this variation stuff works. So the first thing we should think about is what's called a virtual displacement. Oh, I guess one thing I forgot to say in the summary was that once we know the number of degrees of freedom for a system, we can use a system of coordinates that has the same number of coordinates as there are degrees of freedom, and we call that generalized coordinates. So if you have a set of coordinates which we label Qi, to describe a system, and in principle they can depend on t, so they go from I from equal 1 to I equals n. We call this generalized coordinates. Sorry, I forgot to remind you of that. So virtual displacement, so consider, for example, a coordinate Q of t. So let's say maybe it's a system with 1 degree of freedom. We can describe the system with using that one coordinate, which we call Q. For example, a one-dimensional simple harmonic oscillator, right? A mass on a spring, you can describe by one coordinate, and we'll call it Q. So dq, the familiar differential of Q, that's a small change in Q as the result of a small change in time delta t. So that's what we mean by the total differential dq of some function q of t, is that that function changes by an infinitesimal amount dq if you change the dependent variable t by an amount dt. Okay? Delta Q, which we call the variation in Q, is an arbitrary change in Q without the corresponding change in T. So we call that a virtual displacement. In some sense, it's an unphysical change in the variable Q. So let's think of Q as describing, for example, the position of a mass on a simple harmonic oscillator. And so the equations of motion, are given by the math of F equals minus kx equals ma, right? So the equations of motion predict a certain motion of Q as a function of t. And so dq is a change in Q that corresponds to a change in t, whereas delta Q is a change in Q that is inconsistent with a change in t. Maybe it's Q, you push it into the wall where the spring is, or something unphysical. It doesn't have a corresponding change in time with it. That's what we call a virtual displacement. And the whole idea here is we'll work with these virtual displacements. So if you think of the virtual displacement of all of the coordinates that describe a system, there's some limits in how all those coordinates can change. And that's, in essence, how we'll find out what the laws of motion are. So we'll consider these virtual displacements, but then we'll realize that a lot of them are unphysical, and only the physical virtual displacements are allowed is what, in the end, will give us the correct equations of motion, or the differential equations that describe the true evolution of the coordinates. Okay? So let's start with the variation of a function. So consider a function y, which is given by f of x. All right, so y and f are pretty much interchangeable, right? So y is really a function of x, and then x is the independent variable. Whereas y and equivalently f are dependent variables. Consider also a new function which I'm going to call f bar of x. And that's going to be given by f of x plus epsilon, a constant, times phi of x. So epsilon is small and constant, and phi of x is a well-behaved function. So I'm a physicist, I'm not a mathematician. But if I were a mathematician, I would tell you that everything we're doing here is over an interval in x, where f is continuous and differentiable. That's what I mean by well-behaved. And phi of x is also continuous and differentiable. Okay? So let's say that all functions are well-behaved that means they're continuous and differentiable over the range of interest in x. Okay? So we introduce the variation of f, or y, and we'll call it delta y, and we'll define it to be f bar of x minus f of x. And if we look at what we have up here, f bar of x minus f of x is just that epsilon phi of x. Okay, so let's make a little drawing of this to get an idea of what's going on here. Let me draw x and y axis. Let me draw the function f of x. And then let's draw f bar of x. And let's look at what all these df, dy, delta y, where they all are on here. Label f bar of x. So let's look at a point here. So let's look how the function f changes as a function of x. Right. So if I look over this interval that starts at this point, let's consider delta dx So if I change the variable x by an amount dx, the function f of x changes by an amount dy. So that's the normal calculus that you're familiar with. The change in the function f, df or dy, corresponds to a change in x. So it's like moving up the black line. The virtual displacement, delta y, is a change that's not consistent with the change of the independent variable. So it's a change in f without the corresponding change in x. So in this case, it's a jump from the black line to the red line. That's what we call a variation of the function. So we say that delta y is a virtual displacement. So this function f bar is a new function, right? It's different, and of course it depends on phi of x. For virtual displacement, or a variation, we always have that the variation of the independent variable is always 0. So the variation of the independent variable is always equal to 0. Okay? So let's look at some of the properties of this delta operator that we use to signify the variation of a function. Okay? So properties of delta operator. So it's like properties of taking the variation of a function. So let's look at differentiation. So consider d by dx of delta y. Okay. So that's equal to d by dx of delta y, remember, was f bar of x minus f of x. Okay. So if I plug in f bar of x minus f of x, that's d by dx of epsilon phi of x. And epsilon doesn't depend on x, right? So that just gives us epsilon and then d by dx of phi of x. I'm going to call that phi of x prime. So I'm going to use prime to denote d by dx. Okay? So now let's look at the opposite order of operations. So consider the variation of dy by dx. So instead of doing the derivative of the variation, let's look at the variation of the derivative. So the variation of something, so that's, first of all, let's write that in terms of f, so that's the same thing as saying the variation of df by dx. The variation of something is the varied value of the thing minus the unvaried value of the thing. Alright, so the variation of df by dx is the varied value of df by dx minus the unvaried value of df by dx. So it's df bar by dx minus df by dx. The varied thing minus the unvaried thing. So that's equal to, the first term is d by dx of f of x plus epsilon phi of x, that's f bar, minus df by dx. So you can see I'm going to have a df by dx that's going to cancel. And so I'm left with d by dx of epsilon phi x. Again, epsilon's a constant. And so then I get epsilon phi prime of x. And so the conclusion, of course, is that the delta operator commutes with the derivative. So d by dx of delta y is the same as delta of dy by dx. Any questions about that? Alright, so next let's consider integration. So consider the variation of a definite integral from a to b of some function f of x dx. So that's equal to, so it's the variation of the integral, so it's the varied integral minus the unvaried integral. So that's going to be the integral from a to b of f bar of x dx, the varied integral minus the unvaried integral from a to b f of x dx. Okay, so now I can combine the limits are the same, so I can combine the integrands. So I get the integral from a to b of f bar of x minus f of x of course the integral of f bar of x minus f of x, that's the same as taking the integral of epsilon phi of x. Yeah. Of course, that's the same as the integral from a to b of delta f dx. So we have the delta commutes with the integral with respect to x. So we have delta, the integral from a to b of f of x dx, that's equal to the integral from a to b of delta f of x dx. And then the final property, one that we'll use a lot, is how does delta play with the chain rule? So consider y to be a function of f of x, and the function capital F, that's a function of y. So capital F is a function of y of x. So it's a function of a function. So the variation of f of capital F delta f, that's equal to f evaluated at y plus delta y minus f evaluated at y. So the variation is the varied thing minus the unvaried thing. The varied value of f is when f is evaluated at the varied values of y. Okay? And the varied value of y is y plus delta y. So now let's expand this using a Taylor series. So let's expand the first term in particular, f of y plus delta y, using a Taylor series about f of y. Remember, delta y is going to be small. Delta y in general is that epsilon phi of x. In all this calculus, of course, we only consider when variations or differential changes are very small. So if I use a Taylor series, I have capital F of y plus delta y that's roughly going to be equal to capital F evaluated at y plus df by dy delta y I feel like there's a mistake in the notes. It should be a 1 over 2 factorial. Plus a 1 over 2 factorial d squared f by dy squared delta y squared plus higher order terms. So delta y is small. And we'll only consider terms in delta y. So effectively we're going to say delta y squared is roughly equal to 0. So if we consider only terms that are first order in delta y, then we have the thing that we expanded, f of y plus delta y, that's roughly equal to f at y plus df by dy delta y. Now the variation that we're interested in, which was delta f, that was given by what we have above, f of y plus delta y minus f of y. So then if I plug in what we have above for f of y plus delta y, the f of y's cancel, and so I'm left with roughly the first order in delta y, df by dy delta y. And so that is the chain rule for variation. So delta of f of y is equal to df by dy times delta y. And so in all of analytic mechanics, we're only going to care if functions are stationary. And so just like in calculus, we only care if the derivative is 0. We don't care about the second order derivative. We don't need to know if it's a minimum, a maximum, or an inflection point. So it's the same sort of logic that we follow here. All the conditions that we'll have are always on what we call the first variation, or the first order variation, namely only the terms that have delta y. So it's possible that you would have situations where you need to know the sign of it. In that case, the chain rule, you'd have to carry around the delta y squared terms as well. But for everything that we do, we won't care about the delta y squared term. So everything is first order. Okay. So from now on, even though there was an almost equal sign because of the Taylor series, we don't need the higher order terms. So we're going to use this as an equal sign from now on. Okay. Any questions about the chain rule? So let's just do a very simple example of the chain rule. we want, let's say, the variation of cos theta. Okay, and maybe theta is a function of t or something. So theta is a function of our independent variable, which in mechanics will be time, but in math and calculus it's x. And then we wanted the variation of cos theta. So if we apply the chain rule that we just derived, the variation of cos theta is the derivative of the function with respect to the variable, so it's d cos theta by d theta, times delta theta. And so d cos theta by d theta is minus sine theta. Okay? Now, are any questions with the example? Okay, so what if our function above was a function of multiple functions? If f is a function of multiple functions, let's say f is a function of, let's say, y of x and z of x and other things. And what is delta f? So now f, instead of being a function of just y, is a function of multiple functions of x. So if we want the variation of f, we do delta f of y and z. I guess I'll note that I'll try to say z for the letter z, even though it's called z, but sometimes I may call it z instead of z. Alright, but I mean the same letter. Alright, so the variation of f is the varied value. So it's f evaluated when y has been varied and z has been varied, whenever the other things have been varied as well, minus f at the unvaried values of y, z, and whatever else we have. So again, we can do a Taylor series expansion of that first term. So f of y plus delta y, z plus delta z, etc. So if I'm going to do a Taylor series evaluated at y, z, etc., that's going to be roughly equal to f evaluated at y and z, and then it's going to be a partial derivative, di f by di y delta y plus di f by di z delta z, etc. And then for all the variables, and then second order terms as well. The second order terms are going to be like di f by di y times di z. All right, so this is the same thing when you do a Taylor series of a function of multiple variables, right? You have to switch to partial derivative. All right, so that means that when I do the variation of delta f, that first term in the Taylor series cancels with the second term in the variation. And so the chain rule version for when f depends on multiple functions is that delta f of multiple functions is equal to di f by di y delta y plus di f by di z delta z, etc. Okay. So let's do an example. Two in the notes. Compare the differential and virtual displacement of a position vector let's say a particle, and it's described by a position vector r that depends on a set of generalized coordinates q1, q2, all the way to qn. Okay, so we're going to calculate the differential and the virtual displacement of r. So note that the q's are functions of time. Right? So t is the independent variable. It's what we called x just previously. So in principle, r could also be a function of t. Let me add in t. And, so the true differential displacement, dr, so that's just calculus applying the chain rule. So that's going to be it's going to be dir vector by di q1 dq1 plus di r vector di q2 dq2. Just the chain rule and the calculation of the differential according to the calculus that you already know, plus di r vector by di qn dqn. And since r depends on t, then there's a term at the end that di r vector by dt dt. So that's why now, if you did, for example, not part of the problem here, but if you want to know r dot, so the velocity vector for r, so that's dr vector by dt, so it's everything you have here divided by dt, so that would be dir vector dq1, and I have dq1 divided by dt, which we call q1 dot. Remember, dot signifies derivative with respect to time. So the velocity vector would be given by dir by dq1 q1 dot, dir vector by dq2 q2 dot, plus the last q term, which is dir by dqn q1 dot, plus dir by dt. Remember, we saw that last week as well when we were looking at the generalized velocities. Right, we had this dir by dt term at the end. So now the virtual displacement, delta r, applying our chain rule, is going to be dir vector by dq1 delta q1 plus dir vector by dq2 delta q2 plus all the way to dir vector by dqn delta qn, but there is no dir by dt term. Remember, the virtual displacement is a change in the thing without the equivalent or corresponding passage of time, or the truly independent variable doesn't change. So delta t would be 0, because t is the independent variable. Okay? Any questions about that? All right. So next, now we'll start applying some of the stuff. We'll calculate the stationary value of a function. We want to recover the familiar results from calculus using this variational stuff. So what do we mean by stationary value of function? So picture a function, let's say of 2 coordinates, a function s equals, a function of x and y, for example. So you can think of that as a surface in an n+1 dimensional space. Right, so if you have a function of 2 variables, f of x and y, you can draw that in 3 dimensions, and you can think of it as a surface. And so a stationary point of that function f is somewhere along that surface where it's flat. And so you can generalize this into n dimensions, and f can depend on as many coordinates or functions as you want. The idea is that we want to find spots where that function is stationary, and so in our familiar 3-dimensional space, we're talking about a 2-dimensional surface and finding, peaks and valleys and inflection points. So the important thing to know is that for a stationary point of a function, the variation of that function in any direction is 0. So that basically means that the function is flat, and because the function is flat, you can find such a point if, when you're at that point, you move in all directions and the function doesn't change. Okay? So consider a function f, and let's say it depends on a bunch of variables which we'll call q1, q2, all the way up to qn. And so we mean that the qi's are maybe functions of t or x. Either way, the q's are functions of the independent variable. Alright, so for a stationary point, delta f equals 0. So only if I'm at a point where the function is stationary, then you can think of it in like a surface in 3D space. That means the function is flat. So any direction that you walk along the coordinates, the function shouldn't change. So we have delta f, using our chain rule, is di f by di q1 delta q1 plus di f by di q2 delta q2, etc. di f by di qn delta qn. That must equal 0. Okay, so just a reminder in case you missed it the first time around, when I say partial derivatives, I'll use the di for that delta term in the partial derivative. And if I'm doing a total derivative, I'll say, df by dx. So di f by dx versus df by dx. So let's impose, or we can write the virtual displacements So we'll write the virtual displacement delta qi as epsilon times some alpha I. So alpha I is a change of each coordinate, specific to each coordinate, and then epsilon is an overall number to make all those changes small. And I can ask myself, how does delta f change as I change epsilon? So I could say the rate of change of delta f with respect to epsilon that's just given by delta f over epsilon. And so that'll be equal to di f by di q1. And so the delta q1, which was epsilon times alpha 1, the epsilon's been divided out, and so I just have alpha 1 plus di f by di q2 alpha 2 plus di f by di qn alpha n. So now alpha we could write that, say, as a vector, and it's an arbitrary vector in the space of the Q's, right? So it's basically saying alpha is that vector itself is an arbitrary direction along which you go to see if the surface is changing. So if you're at a minimum of the surface, thinking in a 2D surface and 3D space, then it doesn't matter which direction you go in, the function's not going to vary. Alright, so if I write the thing that we have above here, I'll just write it neatly as a sum. That's equal to the sum of I equals 1 to n of di f by di qi alpha I. Remember, that's got to equal to 0. So now, we need this to vanish, so as epsilon gets smaller and smaller, the change in f should be 0. So that means the sum of di f by di qi times alpha I is equal to 0. Now, this must be true no matter which direction alpha we choose. So that means that each term must be independently 0 and independently of alpha. So we find that di f by di qi alpha I is going to be equal to 0 regardless of the choice of alpha I. So that little symbol means for all values of the thing. And so that means that di f by di qi equals 0 for stationary point of f. Of course, that's a familiar result from calculus. If you were given a two-dimensional function and you were asked where are the minima and maxima, you would have taken the partial derivatives of f and set them equal to 0 and use those equations to find those points. So we just did slightly different math than you would have in calculus. Using this calculus of variations, we'll arrive at the familiar result. Of course, this is a more complicated way of doing it, more simply in calculus. Okay. And we do it now for a function so that later it's easier when we do it for an integral. It's easier to understand. Alright, so then the last thing I wanted to cover today are constraints and Lagrange multipliers. So far, when we tried to find the stationary point of f, we said that we can choose an arbitrary direction alpha, and along all those directions, f must not change, so its variation must be 0. And that's the condition for a stationary point. So what we said is that we can vary the q's. So all the delta q's are all independent of each other. They're all epsilon times alpha I, and the alpha i's are independent of each other. So we said we can go in any direction that we want to look at the variation. But sometimes we can't. Sometimes the coordinates are constrained with respect to each other. So one example would be, for example, the position of a point mass that can move around in a bowl under the influence of gravity. So you can displace that mass. Let's say it's at the bottom of the bowl. If you displace that mass horizontally, then it will go through the edge of the bowl and end up suspended inside the bowl or outside the bowl. So that's a motion that's not in harmony with the constraints. So maybe in that case, when you move the ball or the point mass out from the center of the bowl, you have to also raise it if you want that to be a physical displacement. And so there's a constraint that's imposed there on our particle. And so that means that the change in, say, radial position of the particle is not independent of, say, its altitude, its height from the bottom of the bowl. So sometimes we want variations that are still physical, and it's still a virtual displacement, right? If you have a ball that's sitting at the bottom of the bowl, and you displace it along the side of the bowl, that's not a displacement that's consistent with the equations of motion. Right? It's an unphysical displacement for the ball to just suddenly walk up the side of the bowl by itself. So it's virtual still in that sense, and it's unphysical, but it's like not super unphysical as in it goes through the edge of the bowl, but it's still unphysical. Okay? So sometimes we need to consider those cases that are physical, or that are, in harmony with the physical constraints, but not necessarily in harmony with the equations of motion, in which case gravity would tell the ball to go to the bottom of the bowl. Okay? So all that to say that in some cases, when we have constraints, we cannot vary the coordinates independently. So the delta qi are related to each other. Okay, so sometimes, and sometimes means when we have constraints, we cannot independently vary the delta qi. What that means is that some delta qi are constrained. So let's say that let's restate our problem. So we want a stationary value of f, which is going to depend on q1 all the way to qn, subject to the constraints. And the constraint is going to be given by some equation. And I'll write that equation as a function of the variables q1 to qn equals 0. Right. So if I have, the example I gave in the summary of the two masses connected by a rod, and I wrote the distance between the masses positions is equal to a fixed number, well, I can move that all into one equation that's equal to 0, where the left-hand side is everything minus L squared, and then equals 0. We always write a constraint equation as a function of the variables and set that equal to 0. Alright, so this lowercase f is a constraint equation. So the problem is to find the stationary value of f, capital F, subject to the fact that the lowercase f function must be satisfied. So that ties in how you can vary the delta q's with respect to each other. Okay, so the obvious way to do this, so we have the function capital F and the function lowercase f. So we can use the equation that's given by lowercase f equals 0. We can rearrange that equation to solve for one of the q's in terms of all the others, and then we can take that q and substitute it out of the capital F, and we effectively have capital F with one less coordinate in it because they depend on each other, and then we can just do what we already did. That's a perfectly valid way of doing things. It's not the greatest way to do things necessarily because maybe it's not obvious which q you should eliminate. Maybe all the q's are interesting to you. You're describing a system, and there's no one q that's less important than the others, and you maybe don't want to just get rid of one of the coordinates. So you might have to make an arbitrary choice of which q to eliminate. Okay? So there's a way to avoid having to make that arbitrary choice. So let me just say that one could use the f of q1 to qn equals 0, eliminates one of the qi from f, and proceed with n minus 1 qi. But in order to avoid arbitrarily eliminating a qi, we can use the method of Lagrange multipliers. So, because f, lowercase f, is equal to 0, then the variation of delta f is also equal to 0. It's very easy to verify. So that means we have delta of lowercase f, which is just given by the chain rule. So that's di f by di q1 delta q1 plus di f by di q2 delta q2 all the way to di f by di qn delta qn. That's got to equal to 0. Okay. And we also have delta capital F is the same thing with capital F. So applying the chain rule, it's di capital F by di q1 delta q1 plus di capital F by di q2 delta q2 plus di capital F by di qn delta qn. That's also equal to 0. Now the hiccup here is in the second equation. I can't just say all the delta q's are all independent and can be changed independently from each other. And because of that, then all of the di-F by di-Qs must be 0. That's not true anymore. The delta Qs can't just randomly change without affecting the other ones. You know that for sure at least one of the delta Qs, its change is going to depend on all of the other delta Qs. You cannot vary the delta Qs independently. Alright. So, say, di-F by di-Qi is not equal to 0 because the delta Qi are not independent from each other. So let's proceed with this method that was discovered by Lagrange and then really quite clever. So let's build the linear combination. Delta F plus lambda delta lowercase f. So remember, delta capital F and delta lowercase f are both equal to 0, right? So if I add 0 and 0, then, or even 0 plus lambda times 0, I still get 0. Right? So if I write this out, I have the notes are missing lambda. So we have delta capital F plus lambda delta lowercase f. That's just rewriting what I have above. So that's di capital F Q1 by di Q1, delta Q1 all the way to di capital F by di Qn, delta Qn, and then it's plus lambda di lowercase f by di Q1 delta Q1 plus etc. all the way to lambda times di lowercase f by di Qn delta Qn. Okay? So let me write this a little bit more neatly with a sum. So that's equal to the sum from I equals 1 to n of, I have di capital F by di Qi plus lambda times di lowercase f by di Qi, and that all multiplies delta Qi. So far, lambda is an arbitrary number. All we did is we said 0 plus lambda times 0 is still 0. So here's the genius part. So we have a sum here, right? There's n terms in the sum. And they're all of the form di capital F by di Qi plus lambda times di lowercase f by di Qi times delta Qi. Right? That whole sum is equal to 0. Or the delta Qi are not independent from each other. So one of the delta Qi's depends on all the other delta Qi's. So if I set all the delta Qi's to random numbers, one of them is not going to be random. So the step of genius here, well, was to write it this way to begin with. We're going to now choose lambda. So that's the last term in the sum. is equal to 0. So that means that the last term in the sum, so that's di f by di qn plus lambda di lowercase f by di qn, that term there is equal to 0. So it's that term there times delta qn equal to 0. Of course, the delta qn can just cancel here. So now I have di f by di qn plus lambda times di f by di qn lowercase f equals 0. And so we chose lambda specifically to make the last term equal to 0. So now we can write the sum, our linear combination. So that was delta capital F plus lambda delta lowercase f. That's now the sum from I equals 1 to n minus 1, because the last term is equal to 0, so there's no point in writing it down. It's identity 0 because we chose lambda that way. And then we have di capital F by di qi plus lambda di lowercase f by di qi delta qi. Okay. So just note here that the sum now goes up to n minus 1 instead of n. So we can think of the equation above, the one in Qn, we can think of it as the equation that gives us lambda. So we can also think of Qn, well, let's choose Qn to be the special variable that we eliminate. So now, we can vary these delta Qi's, so these n minus 1 delta Qi's independently. Now we can do what we did before. So now every term must be identically 0. Right? We can say that since the sum must be 0, and we can vary the delta Qi's independently, that means that for all I up to n minus 1 only, the term in parentheses is equal to 0. So now, for I equals 1 to n minus 1, we can write that the terms in the sum, di capital F by di qi plus lambda di lowercase by di qi equal to 0 for all delta qi. And so that solves our problem. We have, for the nth term, we have this blue equation here that I'm boxing in blue. And then for all the other terms, we have the second equation. Now compare the two equations. They're identical. It's actually, we wrote it out, we were thinking we were eliminating Qn, And then we got an equation for lambda. And then we looked at the other variables, and then we actually get exactly the same equation. So it doesn't matter if I goes up to n or n minus 1. It's the same equation for all of them. Right? So that's the true genius of this method, is that it tricks you into thinking you're making one of the variables special, but you're not. And then you end up with the same equations for all the variables. So this means that we can rewrite this method a little bit more generally. So instead, consider a new function which I'll call capital F bar. And let's say that function, capital F bar, is defined to be capital F plus lambda lowercase f. So we can find the stationary value of capital F bar instead of worrying about finding the stationary points of F, of uppercase F, subject to the constraints given by lowercase f. So the question is now, you have n variables, so presumably this point in space, where f is stationary, you need to find its n coordinates. And from this method of finding the stationary points of f bar, you're going to get n equations, right? You're going to get a di-f bar by di-qi for each of the n qi. So you're going to end up with n equations, n unknowns that are the position of the point in the space, but then there's this lambda. So you really need one more equation to give you lambda. It's not enough equations. So the final equation that gives you lambda is the fact that lowercase f is equal to 0. So to find this point, so the stationary point of f bar is given by the n equations that are di-f bar by di-qi equals 0. That's n equations. Plus the equation lowercase f of q1 to qn equals 0. That's one equation. And that's good because you have n plus 1 unknowns. With lambda. Maybe, let's see. I have an example, but that will probably take 10 minutes, and that goes all the way to the end of the lecture. But since we went this long without a break, maybe I can start with the example next time, and it'll be a nice transition from the summary. Do people prefer if I do the example now, or?
I'll be waiting for my next class to do it.
People probably want to take a break, right? All right. Let's say people. What, did somebody say something? Okay, so let's stop right there. Perfect. And then the student from BHSU, that's what, Rachel, I saw, I think. Can you just please email me, and I'll give you the information for the course. Thanks. All right, bye everyone. We'll talk on Thursday.